Alright, so we're starting 6.1, which is basic set counting rules and some common experiments that we'll see that we'll have to learn how to count the universal set of and subsets of that you'll see over and over and over again. Alright, so these are your basic counting rules, and then we're going to add to them in the later section, 6.3, 6.4, we're going to add to these basic rules. So you need to have these down before we get to some of the harder rules in the later sections. Alright, we're going to be doing experiments, so it's important that you understand what an experiment is or how we classify an experiment in this class. Basically, an experiment for us is anything that we can do where the result is uncertain. Alright, we usually denote the set of all outcomes in an experiment by S, which we either call the universal set or the sample space. Often, when we're dealing with experiments like flipping a coin, rolling a dice, we call them sample spaces, but universal set works as well too. But that's basically what we're going to do. Anything that's uncertain, like I said, flip a coin, roll a dice, pick a deck of cards. Actually, those are 3 examples that we're going to get to today. But survey freshmen at Illinois State University. We don't know what they're going to say. Randomly pick 3 people in a room. Alright, again, we don't know which 3 people are going to be picked. Now, there's a likelihood that's going to happen, and that's in the next section, chapter 7. But right now, we're just figuring out, well, how many ways can I do something? How many ways can the experiment pan out? Then in the next chapter, we're going to look at, well, what's the likelihood those ways are going to occur? Like when I flip a coin, I've got 2 options, heads or tails. Alright, there is a 50% chance I get heads, 50% chance I get tails, and that's the next section. Right now we're just counting how many results happen when we flip a coin. Well, there's only 2 results that can happen. Alright, that's what we're looking at in this chapter. Alright, so we want to count stuff. That's the whole purpose of chapter 6, is figuring out how many, number of, alright, the physical count of a set. Alright, we have, again, math as a language, we have our own notation for stuff that you have to use and be able to recognize, right, terminology. And so the first one is this number of elements in a set. It's denoted n of a, and again, that would be a number that we'd write down. Alright, if there are 10 elements in set A, if we count 10 elements in set A, that number would be 10. If there are 1,000 elements in set A, that number would be 1,000. It's also called the cardinality. That's just the formal term of it. Alright, so if you see that term cardinality of a set, that just means the physical count. That's it. It's just a fancy term for, we want to know how many. Alright, what's the number of? Yes, and again, we're going to keep it basic in this part, and then we'll do bigger and more broader examples in the next few sections. Alright, like I said, we're going to keep it basic right now so that you understand it, and then we'll add the harder stuff as we move on. Alright, so again, hopefully you get the basic stuff first. Alright, so a simple example of an experiment, like I said, would be like rolling a dice. Alright, I have a die, any dice that you would pick up in a game or something, you'd roll the dice. Alright, so if I roll a fair 6-sided dice, 1, fair meaning it's weighted fairly, then the set of outcomes that are possible on a fair dice are the numbers 1, 2, 3, 4, 5, and 6, right? Those are the numbers on it. If you look at a dice, it's got numbers on each side, 1 through 6, alright? Then the count, the cardinality. Alright, the count is, well, there are 6 things that can happen. There are 6 possible outcomes every time I roll a dice, right? I don't know which of the 6 outcomes are going to happen, but I know I can get a 1 through 6 every single time I roll a dice. So there are 6 possible outcomes, 6 possible elements that I can find when I roll a dice, alright? And so that's what we're doing. We're counting 6. Alright, so we're going to be counting stuff, some methods we're going to be utilizing to count stuff. Alright, so we want to count the number of elements in a set or a subset. We're going to be able to do both, count total number of elements possible or subsets of my total number of elements possible. Alright, one way is going to be listing it. In our first few examples, we will do this. Sometimes it's just helpful to see the set. And if it's a small set, listing them is a good way to go. And then physically count how many is in my universal and how many are in my subsets. We will be using some counting rules in this section. I'll be introducing you to some basic counting rules, and like I said, in the next few sections, we'll be adding to that. Alright, so counting rules. We can use visual aids. Alright, we will get to Venn diagrams in the next part. So I broke 6.2 down into part 1, which are the basic rules of counting. and some common experiments. And then part 2 is specifically looking at Venn diagram cases, where we'll use those to help us count stuff. Or decision trees can be used. All right, we'll do a few examples. We'll do more with trees in chapter 7, but we're going to get your toes wet here in chapter 6. I didn't write this down, but tables are also good tools to help us count stuff. We'll use tables a little bit, probably more again, like I said, in chapter 7, but tables are also good. You can list things in tables, and tables, if we've organized our information well, can help us count stuff easier. Alright, so those are some methods. We're going to start with these two. Alright, list our elements and counting rules. We will do one example of a decision tree. We're going to say Venn diagrams for the next set of notes. And then tables really are more later on, but tables are a good method to do this. Alright, so our basic counting rules. Alright, the complement rule. Alright, we know what a complement is. Alright, we talked about what it is. Alright, the complement is the number of elements not in whatever set I'm looking at. Alright, sometimes it's easier to find the complement than it is to find the set I want to know. Alright, so the complement, remember, finds the number. Now, so this is counting, right? This is counting rules. So it's the number, the count, of the elements not in set A, right? That's what this means. This stands for the number. Alright, that's what that notation means. You have to recognize and be able to read. The number of outcomes not in my set A. We'll figure out how many elements are not in set A. Remember, not in set A means everything in my universal set that do not show up in set A. And so that's what we use. We use our universal set in set A. And so I figure out, well, how many elements are there total? How many elements are there in set A? Throw away, right, subtract the elements in set A, throw them out because I don't want them. What's left over is how many elements are not in set A. Like I said, the complement rule is actually going to be one of those rules that we'll utilize a lot when we get to bigger sets, because a lot of times it's harder to find the set I'm looking for, because there's more things to it, more stuff involved, than it is to find the complement, especially when we get to terms like at least and at most. All right, the complement's going to become your friend in those cases. And so what we do a lot of times is we use this form of it. It's the same thing, it's just switch the rules of set A and not set A. Alright, what we want to find is the number in set A, right? This is the number in set A. Well, we find the number in the universal. And then we throw away the number not in set A. Right? And sometimes this is the easier set to find. We can eliminate elements I don't want a lot easier than the elements I do. And once I throw out the ones I don't want, what I'm left with are the ones that I do. And that's the complement rule we'll be using. So again, this is going to become very useful when we get to some of our bigger sets. Alright, a simple example to get you to understand. Again, this is simple. This is one that hopefully you can see how the complement works, so that when we get to bigger sets, you'll know that it works because you've seen it here in a very simple example. Alright, so again, going back to my rolling my dice, where I've got my sample space, I've got 6 possibilities. The numbers 1 through 6 can be rolled. Those are the number of elements in my universal set is 6, right? There's 6 outcomes when I roll a dice. Suppose I'm playing a game, and in the game, I want to roll a 1 or 5, alright? So that's the subset, that's my goal. Alright, I want to roll a 1 or a 5. So the number of outcomes in my subset is 2. Right, there are 2, and where this is eventually going, that's why we need to know how to count stuff, is, well, how many ways can A happen? How many ways can my subset occur? Well, there are 2 possibilities out of 6, right? 2 chances out of 6 when I roll a dice to get a 1 and a 5. Alright, well, suppose I want to know what's the chance, or the number of ways that I won't get my 1 and 5. Now, again, this is very basic. You should be able to answer this right away. Alright, but I am going to use the rule, number of items not in set A. Well, it's the number in my universal minus the number in my set A. And so the universal had 6, set A had 2, and so there were 4 elements not in set A. Which actually I can list those, right? List them. If 1 and 5 are in set A, that means 2, 3, 4, and 6 are the elements not in set A, and there are 4 of them, right? So The odds that I don't get what I want, which is a 1 in a 5, is 4 chances out of 6. Which again, that's eventually what we're doing. Right now we're just focusing on the count. Alright, can I count how many? Right, and complement's one way we use to count stuff. Alright, the union rules. These are ones, again, you just need to memorize. You'll be using them over and over again in this set, and in the next set, next chapter, and the chapter after that. Alright, the union, remember, is the OR statement. Alright, the number of items in set A or set B. And OR is always the one you have to be careful of, because OR includes the overlap. Alright, and I want to count the number of elements that are in set A or set B. Alright, so that's what this is. Alright, and so the rule is, I add the number in A plus the number in B, right? OR is all inclusive. But then there's this very important step where I have to subtract. Alright, and so I have to subtract any elements that showed up in both A and B. Alright, so let's understand this. Why do I have to subtract the number that show up in A and B? Well, the reason why is set A and B can have common elements. Right? They can have overlap. There can be elements that are in both set A and both set B. So when I counted set A, I could have counted the same element in set A that I did in set B. Well, that element would get counted twice in that case. Alright? Alright, so we don't want to. Alright, we never want to count elements twice. Alright, and so to get around counting elements twice, that is why you subtract the number in A and B. Alright, and we'll look at a simple example to sort of, again, give you an idea of why this is the case. Alright, but the case is, if they've got elements in common, so A shared some elements with B, when I counted the number in A, I counted the same elements, again, when I counted the number in B. And so that means those elements were counted twice, right? Which means I count them as two separate objects when they're not, they're just one. And so then what we do is, well, we subtract one of those counts, all right, and to figure out how many times we counted things twice, well, we figure out how many elements were shared in common. That's what this AND statement means. All right, so I subtract the number of elements that they shared, right? That's what this is. I subtract. You can read this. I subtract the number of elements in common. Alright, and that means I won't count anybody twice. Alright, so to understand this, again, like I said, in a basic example where you can see it, because we're going to get to examples where we can't. We're going to have examples where we have hundreds, thousands, millions of cases, and we can't list them. Alright, so we're going to start with a simple case where we have listed a few elements. Alright, so I've got my set A, which has the elements R, S, and P. So the letter R, S, and P is in set A. Set B is the letters T, S, and M. I want to count the number in A or B. And again, you could do this without, but I want to show you the rule, how it works. Alright, so the number in A plus the number in B minus anybody that got counted twice, any elements they share, minus the AND statement. Alright, there are 3 elements in A, there are 3 elements in B, and they share the same element, S, right? Both sets have S. So when I counted the 3 here, I counted S. And when I counted the 3 here, I counted S. But there is only one letter S in the alphabet. If I leave it without subtracting that one letter that they share in common, I'll get the wrong answer. Alright, they share one letter that I counted twice. And so the number of elements that are in A or B is 5, right? There are 5 different elements in the set A or B. Alright, and I can list them. Right, those 5 elements are R, S, P, T, and M. And I don't list S twice because there's only one letter S, and so that's it. There are only 5 different letters I can pick if I'm picking from set A or set B. Right? And so when I'm counting, I have to be very careful. If they shared any common elements, I gotta make sure I didn't count that sucker twice. Alright, the next rule is a little nicer. Remember I said before we like things that are disjoint? Alright, this is one example of why we like things that are disjoint. Alright, suppose we know, we're told, or we can look and see that we've got disjoint sets. Alright, set A and set B, we're told they're disjoint. Now we want to count the number of elements that show up in set A or set B. Alright, again, the or statement's the one we have to be careful of, but in this case, I'm okay. Alright, you'll notice number of elements in set A or B is strictly number of elements from set A plus the number of elements from set B. Alright, we no longer have to subtract the number of elements in set A, and the reason why is because that term disjoint is very, very important. Alright, that term disjoint means there are no common elements. Alright, that's what disjoint tells you. It means the number in A and B is 0, right? It's empty. There are no elements in A and B. They don't share anything. And so I don't have to subtract, because if I did, it'd be subtracting nothing. Alright, so I don't have to worry about it. Disjoint sets are nice. Alright, so a simple example of disjoint sets. So I've got set A and set B again. Alright, but I've got different letters this time. A is the letters W, X, Y. B are the letters T, M, and P. And so they're disjoint, right? These are disjoint sets. They have no common elements. None of the elements in A show up in B, and since that's the case, it's just the number of elements from A plus the number of elements in B. I don't have to worry about subtraction. Alright, there are 6 different elements in the set A or B, right? There are 6 different letters that I can choose from if I'm choosing from set A or set B. Alright, those 6 letters would be X, W, Y, and I don't know why I wrote it in a different order, and T, M, and P. Right? So that's the difference between disjoint, no overlap. Straight count. Not disjoint, I have to watch out for the overlap, and I can't count anybody twice. I have to make sure I do a subtraction step. Alright, so again, like I said, that's very important that you recognize the 2 cases. Alright, a simple example. Alright, so we were doing simple examples where you could see the sets, alright, where I listed them. I had a list of what was in A, I had a list of what was in B. Well, this is an example of where you don't know what the elements are. You just know in the universal set there are 12 different elements, right? Set S is my universal set. We also know the number of elements not in B is 5, the number of elements in D is 8, and the number of elements in B or D is 11. All right, find the following. And so this is getting you to use your rules. All right, I have to use my formula rules to answer both these questions. All right, I want to find the number of elements in B, so this requires my complement rule. All right, I was given my universal set and the complement to set B. And so I take the number in my universal minus the number not in B, and what I'm left over with is what I want. Alright, so there were 12 elements total. 5 of them were not in B, which means 7 of them have to be in B. Alright, so the number in group B, or set B, is 7. Alright, if there are 5 of the 12 not in B, means 7 of the 12 have to be in B. Alright, now, we didn't have the AND statement as a rule, right? We didn't have the intersection rule. What we had was the complement rule and 2 union rules. But in the union rule, my intersection is involved, right? If we go back and look at the first union rule, the number in B or D, right? I'm given, that's why I'm using B or D. Well, the union rule would be the number in B plus the number in D minus the number in B and D, right? And that's what we're looking for, right? This is what we want to solve for. All right, so I use my union rule formula. I'm just not solving for the union. I'm solving for the piece of the formula that's the intersection, right, which means I should be able to fill out everything else in that formula. And I can. They gave me the or, that's 11. All right, so there's 11 elements in B or D. I just found the number in B, that was 7. They gave me the number in D, which was 8, and I'm looking for, well, how many did B and D share in common? Alright, well, if there are 11 elements in one or the other, 7 plus 8 will add up to 15. Alright, which is more, I know there's got to be some overlap because there aren't 15 different elements, there's only 12. And of the 12, only 11 of them land in B or D. And so how many did they share? Well, what do I have to subtract from 15 to get to 11? Well, I have to subtract 4, right? This has to be 4. Alright, 15 minus 4 will give me my 11, and so the answer is 4. There are only 4 elements that are shared between B and D. Alright, and so that was an example of using our rules. Alright, so the last rule in this set of notes is the Cartesian product rule. Alright, so the Cartesian product we sort of touched on a little bit earlier. The Cartesian product is when I'm taking two sets and pairing them together. And we'll do this when we flip coins, roll dice, and things like that. We'll pair stuff together. Alright, so I've got set A, which has so many outcomes, set B, which has so many outcomes. When I want to pair them together, remember I'm selecting an element from set A and pairing it with an element from set B. Alright, I want to know how many outcomes are possible, how many pairs are possible. Well, the name kind of gives it away. Alright, it's a product of the two sets. It's the number of my elements from my first set A that I'm picking from, and then times the number of elements from my second set B. Alright, so a simple example, I've got set A here, and set B. Alright, set A is the letters X and Y, set B is the letters T, M, and P. And so there are 2 elements in set A, and 3 elements in set B, and so that means there would be 6 outcomes. Alright, 6 pairs of points total. Alright, I'm going to list them just so that you can see them. Alright, which again, we did practice this last time. So the pair point, remember I pick an element from set A, pair it with all the elements from set B. Alright, so my first point would be X can be paired with T, M, and P. So X gets paired with T, that's one outcome. X gets paired with M, that's another outcome. X gets paired with P, that's a third outcome. Alright, done with X. Now I do Y and pair it with all 3 elements in B. So Y gets paired with T, Y gets paired with M, and Y gets paired with P. And if you count those, there are 6 total outcomes. Alright, so if I pick something from group A, pair it with something from group B, 2 elements from A times 3 elements from B. Cartesian product rule is we multiply, and there should be 6 total outcomes possible. Alright, so those are the basic rules. So we got to make sure we have these basic rules down before we get to the harder rules. So in the next video, the second sort of video for this set of notes, next videos, are going to be going through common experiments where we have to count stuff. Alright, we're going to look at common experiments. So make sure you've got these rules down, because we'll be using them, like I said, over and over and over again. Alright, so make sure you look this back over and understand them.